So in this lecture, we're going to talk about processor, control, and data path. That is, how do we actually build the processor, and how do we control the parts that we've built? So there are two basic parts of this lecture. The first part is going to be what are the pieces in the processor, and the second part is going to be how do we put them together. So the pieces we're going to look at are instruction access, that is, how do you go get the instruction, the ALU operations, how do you actually do the work such as the addition or subtraction, and then memory operations, how do we load and store data to the memory. We're then going to put all these together, and there are two things we need to look at there. The first is the control signals and how do we route them. So how do we send signals around the processor to control what the various pieces do, and then how do we decode the instructions to figure out how to set those control signals. Finally, in Lab 3, you're going to get to put this all together. So in Lab 3, you're going to get to build a logical part of the processor and see how it works and make sure it all functions. So what am I not going to cover now? I'm not going to cover the ALU function fields in great detail. This is covered in the book, and you're going to need this material for the lab, so you should take a look at it. So we're going to do a basic MIPS implementation. It's going to be a simplified subset, which just makes it easier for us to work with, but it's going to cover all the important parts. So we're going to look at memory instructions, load and store, some arithmetic instructions, add and subtract, some logic instructions, and simplified branches, so just branch equals. We're not going to look at jump. So what is missing? Well, I mentioned we don't have jump. We also don't have multiply and divide. We don't have a bunch of the logical operations. There's no XOR in here or NOR. We don't have jumps, and we don't have jump return and jump and link. So for the unconditional jump and jump return and jump and link, we're going to look at some of those things later in the practice problems. So let's get started with what we're going to design. So the first part of what we're going to design is the instruction fetch. This part has to figure out which instruction to load and then load it from the memory. Then we're going to look at the ALU operation. This is going to figure out which operation to do. So should it be an add or a subtract, and then actually do it. And then finally the memory access. And the memory access needs to figure out which address to access and then go ahead and access it, either a load or a store. So let's take a look at this. Here's our instruction fetch. It's going to give us an instruction. The instruction is then going to be used the ALU to do some work, and the result of that is going to be computation, some result that we've computed, and then we're going to go to memory. So this allows us to actually run a program. Now let's look in more detail at the parts of these various boxes. So for instruction fetch, we have a program counter. We've mentioned this before. This is what stores the current instruction address. We're going to have a program memory. That's where we're going to store our programs. And we're going to have some logic. So this logic is going to calculate the next instruction. And it's going to handle whether we're doing a jump or not doing a jump. Now you'll notice how these are color-coded. The orange boxes here are state. Those are memories that get updated with the clock. The purple box here is combinational logic. So remember, this combinational logic doesn't use a clock, it just has inputs and outputs. Let's take a look at the ALU operation. So obviously we have the ALU itself. This is the part that's going to do the addition or the AND or the OR. And we have a register file. And remember, all of the operations in MIPS come out of the register file. So the ALU is going to use the register file to get its inputs. And then we have some operation decode logic. This is the logic which takes the instruction and figures out which ALU operation to do. Finally, for memory access, we're going to have our data memory. Not surprising, we want to store data. And we're going to have some combinational logic that determines the address. So we need to figure out the address that we're going to use to access the data memory. So here are the parts we're going to build. And if you look at this, something is missing. And what's missing is that we've gone ahead and we've created a result, and we can write it into memory, but we don't have any way to get the data from memory back to the ALU. So we're missing this path here, something from the memory so that we can write data into the register file so we can work with it. Now, the first design we're going to do is going to be a single cycle design. That is, every instruction is going to be done in one clock cycle, or we're going to have one clock cycle per instruction. This will simplify things, but it's not going to be high performance. We're going to talk about in the next lecture how we pipeline the processor to get higher performance. So let's remember how we design this sort of logic from our logic lecture. We have combinational logic that generates the next state. We have memories that store the state. So these can be latches or RAMs. And we have a clock. And the clock transfers the next state to the current state and then we go and we run around the loop again. So we use a combinational logic to generate a new next state, and then on the next clock we store it. So if we look at the picture we had before, we have our current state in memory. This is outputting the current state, and we have our next state logic. Current state goes into the next state logic, and the next state logic generates the next state. Then we have a clock, and when the clock comes in, we take that next state and we convert it to the current state. We also have inputs and outputs from this logic. So that's the design we had to be started with. Now let's take a look at that in the context of a processor. So how are we going to use this design for instruction fetch? That is, getting the next instruction. So what's our next state? Well, our next state is going to be PC plus 4, because we go on to the next instruction, which is 4 ahead in the address, except for jumps. So let's ignore jumps for the moment. And what's our current state? Well, our current state is our program counter. That's the instruction we're on currently. So here's a picture of that. We have our program counter, that's our current state, and we have an adder, which is going to calculate our next state. So here's our next state logic. It's just an adder. It takes the current state and adds 4 to it. And of course we have the clock, which goes into the program counter. So here's a question. What is this output right here? It's coming out of the program counter and it's going into the adder. Is this the current state or the next state? So this is the current state, because remember the program counter is our state memory that stores our current state. How about this output here? It's coming out of the next state logic and going into the state memory. Is this our current state or our next state? Well, based on the argument before, this should be the next state. So we've taken the current state, we've run it through our combinational logic to generate the next state.